Hi everyone. This is Unit 9 or Lab Simple Linear Regression, Frequency Approach and Bayesian Approach. So let's practice on Frequency Approach and Bayesian Approach on some real data set, which is uploaded on Canvas, house prices. So first you need to upload the data. You need to run library, read X1, XL, run this one, and then upload the data. After you download from Canvas. And then let's look at this data set, how many variables it has and so on. What are these variables? We have 1, 2, 3, 4, 5, 6 variables. The response is the price house, but there are many explanatory variables like the size of the house, the size of the lot, the number of paths, number of bedrooms, taxes, and so on. So we're gonna select the price as a response variable and the size as the explanatory variable. So let's fit the regression equation. Y equals beta 0 plus beta 1 size using frequency approach and Bayesian approach. I will change the house price to be by thousands of dollars. So I will divide it by 1,000, and this one is the column number 4, 1, 2, 3, 4. And then I will select the size as explanatory variable. And then I will plot the scatter plot of the size and price, because it's very important that the relationship between these two variables to be linear. Otherwise, you should find some other functions to fit the regression equation, because we are going to use LM, linear model function. So let's look at the scatter plot. The relationship is linear. So I can fit the regression equation. So use LM function and then give the response variable and then tilde and then the explanatory variable and save everything under any name. And then summary. And this is summary that I went over in the lecture note, and I explained all these numbers. And then let's graph the residuals. This one is called residual plots. So I will, when you write down plot model, you plot the residuals plots. Let me show you these residual plots. There are 4 residual plots, are very important. The first one is fitted versus residuals to see there is some the equal variance is satisfied or not. And we explained this one in the lecture note, and we said there is equal variance is satisfied. The second one is QQ plot. This one shows the normality is satisfied or not. And we found that it is satisfied. I will show you also a test, Shapiro test, but there are many other tests if you are interested, like Anderson-Darling test and many others. The third one is fitted values versus the squared studentized residuals. This one to see there is some outliers in the y-axis or not. And the R label these values like 68, 35, 64 is not necessary to be outliers, but R show you these values to think about. Maybe those are outliers. But I do not see if they are greater than, 2, so, or less than -2, so it still is okay. The last one shows the outliers in the x-axis, and this one is the residuals versus the leverage point. So I see you should think about this one, maybe the outlier in x-axis, maybe this one, and you should think about these ones, but I see they are okay within the range. And then let's test the assumptions. The first one is, let's see the graph of the equal. If you'd like to graph the fitted values versus residuals, you can graph it using this one. See, if you'd like to see only this one. So there are many ways to get the same thing in R. So let me remove this one to have it on a big one. Plot. And this is the 0 line. Looks like everything is fine. There is no pattern. There is no 4. So equal variance is satisfied. The second one, we covered the graph and also the test. So QQ norm and the straight line looks like it's fine, but maybe those ones are outliers. Let's see, maybe they affect the normality. So you look at Shapiro test. Shapiro test, p-value is big, so normality is satisfied. If you'd like to graph the residual versus the order of the residuals, you can work with the plot model $sign residuals. It gave me the order versus the residual value. So this is the order versus residual values, and let's graph the zero plot, zero line, sorry. And I don't see any kind of form, so it looks like the independence is satisfied. But if you would like to do a test, there is a Durbin-Watson test, which is available in the library car. If you haven't installed the car before, so you need to uninstall car package first and then library car. And then Durbin-Watson gives the name of the model. P-value is big. It means independence is satisfied. So now let's cover Bayesian using the RGEX package. So let's upload the RGEX package first and upload the data. We already uploaded the data. Let's see, maybe someone of you will start from this one. So you need to upload the data first. But you already uploaded this one, but just in case. So let's upload the data again. The head, the same variables. And then let's change the price to be by thousands. And then the size, select the size as explanatory variable, and then the scatter plot. And I need the n, the number of values, or the number of cases, or number of observations, or number of houses in the code. So I use n as the length of price, or length of size, or how many cases we have, how many houses we have. So let's see how many houses. We have 100. And then let's define the model. Let's talk about this one. When you define the model, you give a name, and then equal, and then between quotation, you write down the model. How do I define the model? You always defining the model as two steps. You need to define the data distribution, and the R function will use this data distribution to change it to be likelihood. And you need to give the prior distributions. So you need to give the data distribution, prior distribution. The distribution of the data is normal. So every value, every yi follows normal distribution with mean mu I and tau square. You shouldn't give sigma square, because the RGEX works with tau, the precision doesn't work with sigma square. It's very important. So every price I is randomly selected from normal with mean mu I and tau square. And mu I is beta 0 plus beta 1 xi, but let's use beta 1, beta 2. Why? Because I would like to have the two priors in only one loop. So mu I, but you can make it beta 0 plus beta 1 size I, it's up here. Mu I is beta 1 plus beta 2 size I. And then you define the priors. I will define the two prior distribution in only one loop for j in 1 to 2. Beta 1, beta 2, both of them follows normal distribution with mean 0, and precision is very small. Precision very small, it means variability is very big. It means non-informative prior. So I will assign beta 0 or beta 1, beta 2 or beta 2, beta 1, like you can call it beta 0, beta 1, or beta 1, beta 2. You gave normal distribution with mean 0 because I have no information about the value is what, because I have no previous information. If you have previous study, you can use this previous study to make a conjugate prior informative. But I have no information, so I will use non-informative prior for beta 0, beta 1, or beta 1, beta 2. And then I give the relationship between tau square and sigma square, because I'm interested in sigma square, is not tau square. So you give a prior distribution for tau square as gamma distribution, not inverse gamma, with alpha 0.01, beta 0.01, so non-informative prior. It is conjugate, but non-informative prior. And sigma square, the one I'm interested in, is 1 divided by tau square. So I gave prior distribution for the betas, I gave prior distribution for sigma square or tau square, and I gave the relationship between sigma square and tau square. This is the model. So let me run the model. And then we need to compile the model and ask R to randomly select some initial values. Initial value for beta 0, initial value for beta 1, initial value for beta for sigma square. Initial value for beta 0, initial value for beta 1, initial value for sigma square. And I would like to have 3 changes for each parameter. You can change this when it's up to you. And I gave the data because this model is a function of what? Function of price. I see the price, so you need to know, so you need to give the code what is price, n, function of size, and so on. So you use the function jax.model to compile the model, this model, and you give the name of the definition of the model, and then give the number of chains, comma, and you give the data, the price equal price, n equal n, size equal size. So let's compile the model and see everything is fine or not. He said initializing model, so the model is fine. There is no problem at all. Otherwise, he give you some error. So now we need to update. We need to run the iterative procedure. You can update everything 1 time, 2nd time, 3rd time. How many times? I would like to ignore the first 10,000 of observations because maybe the conversions didn't happen at this time. And then I will select 20,000 more for each chain. So in total, I will ignore each first 10,000 from each chain, and then I will continue 20,000 more. So in total, I have 30,000 for each chain. So in total, I have 30 times the 3, 90,000, but I will ignore the first 30,000, 10 from each. So in total, I will have 60,000 observations or 60,000, a sample of 60,000 randomly select from each posterior distribution. And I would like to ask R to save the beta random sample and sigma square random sample. Maybe I'm not interested in saving everything. Maybe I'm interested in only sigma square. So I will ask the variable names that you need to save their random sample. The only ones I'm interested in, but I'm interested in beta 1, beta 2, and sigma square. So the first one is update. The first, randomly select the first 10 and ignore them. And then you start the samples after the 10,000. And then you select 20,000 more for each chain and save for beta 1, beta 2, save for sigma square. And you give the model that you updated. So update, no errors. The posterior samples, no errors. And let's look at the numerical summary using the 60,000 observation for each parameter. The posterior mean, posterior median, 95 credible set, and so on. So I have 3 parameters. I have beta 1, beta 2, sigma square. This is the posterior mean of beta 1, posterior mean of beta 2, which is posterior mean of beta 0, posterior mean of beta 1, and the posterior mean of sigma square. This is the standard deviation of the samples. This is the naive standard error. It means the standard deviation, this column divided by, each divided by the square root of 60,000. And this is the time series standard error. It doesn't divide by the square root of the sample size. It divides this column by the square root of the effective sample size, because the effective sample size take into account the dependency. Because maybe we have much dependency, autocorrelation in my sample, so the effective sample is small. And what about this one? This is the 2.5 percentile, 25 percentile, 55 percentile, 75, 97.5. The first one is the lower limit of the 95% credible set. The last one is the upper limit of the 95% credible set. So beta 0 or beta 1 is between negative 12.12 and 30.3. So the lower limit is negative, upper limit is positive. So it means we fail to reject H0 because 0 is one of the possible values in the credible set. For beta 1, the lower limit is positive, upper limit is positive. So we reject H0 because 0 is not one of the possible values in the 95% credible set. The sigma square, the lower limit is positive, upper limit is positive. It means the sigma square doesn't equal 0. This is how do I use the 95% credible set to reject or fail to reject H0. But actually, I also can calculate the p-value if I want. And then where we stop? Keep in your mind, we haven't checked the convergence yet. So I shouldn't say this conclusion unless I look at the convergence. So let's look at the effective sample size. One of the measures for the convergence. It should be a few thousands. This one is 3,700 is fine. 3,800 is fine. 56,000 is fine. So looks like convergence happened because the effective sample size is fine. But I should look at the Gelman-Roppen plot. So let's look at the Gelman-Roppen plot. One of the good methods to check the convergence. I see they are very close. I see it graph after the graph the 20,000 to 40,000, and it is the highest value is something like 1.35, which is not fine, but it looks like convergence happened after 22,000. So this one is happened after 21,000 or something. This one happened after 20. This one is okay, 1.04. Looks like it happens at 20,000. But it means I need to change the Pern and values. I need to increase them from 10,000 to 20,000. But looks it's not that much bad. It's not that much big, but it's fine. It's fine. So let's look at the plots. Let's see the convergence happen or not using the trace plots. So let me remove this one so I can have some space and it will be more fast. Let's look at the trace plots. Maybe convergence happen if I see the 3 chains of each parameter mixed well, so convergence satisfied. It takes some time. Guys, I hope the course is good so far. If you have any question, please let me know. So when I look at the beta 1 or beta 0 in the model, looks like it's very good one. Is convergence happen and they are mixed very well. And this is the graphical representation of the posterior distribution of beta 0 or beta 1 in the model, beta 0 in the model. The trace of the second coefficient, very well, very smooth and very good. Normality satisfied, looks like normally distributed. And the last one, the third parameter is sigma square. Looks like they are mixed very well and a little bit skewed to right because sigma square follows inverse gamma, which is skewed to right. So looks, everything is fine so far. And let's look at the comparing with the frequency approach, because I see this is the estimation of beta 0, this is the estimation of beta 1. Let's compare this one to the frequency approach. They should give very close estimation because I haven't added information in the priors. So I gave non-informative prior actually. So let's see, this one is 9.06 and this one 0.077. They are very close to each other because I added a very little information in the prior distributions. And we haven't looked at the autocorrelation plot. Let's see the autocorrelation plot for the 3 parameters. Looks like there is some dependency, like the leg 1, there is some dependency, is about 0.9. The second leg 2 is about 0.8. There is some dependency. It means you should select more sample, but actually the sample we selected is enough, because we found that the effective sample, each effective sample is a few thousands, which is good. For the sigma, because when you look at the effective sample for sigma is very big, because there is no much autocorrelation. So the effective sample equal the nominal sample, or the sample size. But for beta 0 or beta 1, for the first sample, for the first chain, and also this is the second chain and so on, because there are many graphs, the 3 graphs for each chain. So it looks like there is some dependency. This is why the sample size doesn't equal the effective sample size. But this one is fine. This one is fine. A few thousands are fine, can be used to estimate the parameters and also do inference. But this one again is very big, because there is no much dependency in the samples. So thank you so much and have a great day. Please, if you have any question, let me know, guys. Thank you.